Similar to the reaction with water, carboxylic acids can also react with alcohols. You just add a little bit of heat and acid, and this is again an equilibrium reaction, but it does tend to go further this way because you just add a lot of that and it pushes it this way. So what you can end up doing is you can make instead an ester. So this is an ester where you have some carbon over here, a C-double-O bond, oxygen, and some more carbons over here. So an ester doesn't have that hydrogen over here. Instead, it has carbons. Another more specific example is if you have 1, 2, 3, 4 butanoic acid react with isopropanol under acid and heat. See how this basically makes that happen right there? Where you get the water from is if you want to consider this OH coming off along with this hydrogen. See how that would make H2O? Even though that's not really the case, that is sort of how you can think of it. Now, naming esters, these guys can be tricky. So I want to go back and sort of tell you how to name those carboxylates that we talked about last time. So remember, this is ethanoic acid. I'm going to start here in the middle, sorry. Ethanoic acid, because we have 2 carbons. Take off the E, we add oic acid. Well, by removing this hydrogen, that's an ethanoate. So instead of being oic acid, it's an O8. And then here's how I remember it. Because the O ate the hydrogen and it went away, that's how we get an ethanoate. Okay? So this would be sodium ethanoate. Great. Now let's apply that to organic molecules. When we have an ester, we've got an R group over here instead of having sodium over here. So this, the thing that's connected to the oxygen, becomes our substituent. So this is methyl ethanoate. See how this is the thing that's connected to that oxygen? That's isopropyl. And then we've still got 3 carbons here, so propanoate. It doesn't even have to do with the length of the chain. So let's say that I had something even more complex. Let's see if we have 1, 2, 3, 4 over here, and that right there. This would still, this oxygen is connected to 1, 2, 3, 4 carbons. It's still the substituent. So in this case it would be butyl, and this is still ethanoate. So those still are different. This would be ethyl butanoic, so this is just the opposite. See how in this case the carbon chain is 1, 2, 3, 4, and that's what's connected to the C-double-O bond. And in this case it's only 2, and that's what's connected to the C-double-O bond. You can also do this with the benzoic acids that would turn to benzoate, and then this becomes an ethyl group, so it's ethyl benzoate. Okay. Now, since esters do not have hydrogens anymore, they don't have hydrogen bonding, but they're still polar, they're not going to have as high of boiling points as what we saw with carboxylic acids. So, just to give you an overall view again, our nonpolars like alkanes, alkenes are going to be sort of here. And then you're going to have your polar type of stuff. So esters, ethers, some aldehydes could go in that, ketones, but it depends on right there. Alcohols, hydrogen bond, that's going to be next. And carboxylic acid, since there's more hydrogen bonding, will be in the highest bit of that. Esters can still dissolve in water, but they need to be small. So they're not highly soluble in water, and they can't really, they're just not going to be that soluble in water. However, remember, this is an equilibrium reaction. See how this is the exact same thing as what we just looked at a little bit ago? So I'm going to put that underneath. It's just backwards. So we said to start with a carboxylic acid and we added an alcohol, you'd end up with an ester and water. Remember, that's an equilibrium. So the opposite is true also. If you add large amounts of water and you have an ester, then it takes it back to a carboxylic acid. What really drives this, and you can tell which direction it's going to go, if you add water, it'll go to the carboxylic acid. If you add this guy, it'll go back this way. That's called Le Chatelier's principle, and it's very, very useful, but we haven't talked about that in this class. You can also just add a strong base, such as lye, and this will make soap. And we'll talk about that in a little bit later, but this is a base hydrolysis, is another way to refer to it as a saponification. And this will result in a COO minus with an Na there as well. So very similar to what we saw with NaOH and carboxylic acids earlier. Great, thank you very much.